All right, welcome to the Explainer. Today, we're diving into a fuel that's a total paradox. It's the most common thing in the entire universe, it's what keeps the sun burning, and it could be the key to a zero-carbon world. But, and it's a big but, hydrogen has this secret life. A split personality that makes it beautifully simple and at the same time just unbelievably complex. And this quote, man, it just nails it. For the better part of a century, scientists have been obsessed with this contradiction. I mean, on the one hand, you've got the simplest atom there is, right? One proton, one electron. Easy. But the moment you try to actually burn it, its behavior becomes, well, let's just say it's got a mind of its own. And here's that paradox in black and white. If you measure its energy by weight, hydrogen is an absolute champion. It packs almost 3 times the punch of gasoline. That's fantastic for something like a rocket where every ounce matters. But if you look at its energy by volume, it's a total lightweight. To get the same energy as 1 little liter of gasoline, you'd need somewhere between 3,000 and 4,000 liters of hydrogen gas. It's like it's full of energy, but it's also mostly empty space. So what is going on here? Why is the universe's simplest element such a drama queen? Well, the secret isn't really about the hydrogen atom itself. It's all about what happens in the milliseconds after it starts to burn. It all boils down to this one idea, the crossover temperature. Let's call it TC. The best way to think about it is as a personality switch. For a typical hydrogen-air mixture, that switch gets flipped right around 943 Kelvin. That's about 670 degrees Celsius. Below that temperature, hydrogen acts one way. But you push it past that point, and it becomes a completely different beast. So what is this personality switch? It's basically a changing of the guard, chemically speaking. You have these different teams of molecules called radicals that drive the reaction. Below that crossover temperature, the reaction is managed by a pretty chill, slow, and stable team. But once you get above that temperature, bam, a new team of super aggressive, highly reactive radicals, H, O, and OH, takes over. And this team doesn't just react, it triggers a chain reaction that is incredibly fast and explosive. And understanding this switch isn't just some science trivia, right? This has massive, real-world consequences, especially for safety. And that brings us to one of the most legendary and, frankly, weirdest charts in all of combustion science. The S-shaped explosion curve for hydrogen. Okay, so your gut instinct tells you that if you take a flammable gas and you squeeze it, you add pressure, it gets more dangerous, right? More molecules crammed together means a bigger boom. Makes sense? Yet, well, with hydrogen, common sense kind of goes out the window. So let's look at this. At really low pressures, any reaction just fizzles out. And at really high pressures, it does what you'd expect. It gets more and more explosive. But then there's this twilight zone in the middle, where the complete opposite happens. As you increase the pressure, the hydrogen actually becomes less likely to explode. It gets safer. What on earth is going on? Just let that sink in for a second. You squeeze it, and it gets safer. It goes against everything we think we know about how fuel works. But the clue to solving this whole mystery is something we've already talked about. You got it yet? It's the crossover temperature. That bizarre safer zone is the personality switch playing out in real time. In that specific pressure range, the reaction is basically being forced to stick with that slow, stable chemical team, even as the temperature is trying to climb. The pressure itself is flipping the switch back, changing which chemical pathway is in charge, and making the whole system more stable. It's just wild. And the weirdness doesn't stop there. Its flammability range is huge. It can catch fire when it's just 4% of the air, or a whopping 75%. It can keep a flame going in channels so tiny they'd immediately snuff out other fuels. And maybe the most concerning part, it's way more likely to jump from a relatively slow burn into a full-blown violent detonation. This fuel just refuses to play by the normal rules. So with all this craziness, how in the world do you actually use this stuff? How do you reliably start a hydrogen engine when the fuel's behavior is so all over the place? Well, turns out you need a pretty special toolbox for that job. And wow, what a toolbox it is. You've got everything. For something huge like the Ariane V rocket, you might use a big one-shot pyrotechnic charge. For an engine, a good old spark plug can work. But then you get into the really cool stuff, like super precise lasers that can start the fire in the exact right spot, or even acoustic systems that use powerful sound waves to create the ignition heat. It's all about picking the right tool to manage hydrogen's very specific personality. But that's only half the battle. What about the other side of the coin? How do you stop hydrogen from igniting when you absolutely do not want it to? This is without a doubt the biggest challenge for hydrogen safety. This quote just perfectly sums up the engineering mindset here. Look, hydrogen is a tiny, slippery little molecule, so you have to work from the assumption that it's gonna leak. The real question isn't if it leaks, it's what happens next. How do you know if that leak is gonna catch fire? And this is where the engineering gets so smart. Trying to simulate a full-on hydrogen fire is incredibly difficult and expensive, so instead they do something much faster. They run a simple simulation of just the leak. No fire, no combustion. Then, using all the principles we just talked about, they calculate the potential for a fire at every single point in that cloud of gas. They track a kind of danger score that shows where that aggressive, explosive team of radicals is likely to form. If that score gets too high anywhere, you know you have a problem. And you can find that risk without ever having to simulate a single flame. It's brilliant. So in the end, it's not that hydrogen is just dangerous. It's that it's deeply complex. Once you get a handle on its split personality, that crossover temperature, the two different chemical teams, you can actually harness it. You can build incredibly powerful engines, and you can predict safety risks with amazing accuracy. It's only when it's misunderstood that it becomes a real hazard. Knowledge is what tames this beast. And that brings us to the big question for the future. We've just been talking about pure hydrogen. But as we move towards a hydrogen economy, we're going to be blending it with other things like ammonia or natural gas. Are we really ready to figure out the brand new, even more complex personalities that are going to come from those new fuel blends on a massive global scale? That's the challenge ahead.